Alright, so let's try this again. I just opened up ABAQUS CAE. I'll go into the parts and I'm going to create a part. It's going to be a 3D deformable solid. It's going to be an extrusion. We're going to punch in the coordinates for the cross-section dimensions of the corners, and we're going to extrude it out in the Z direction. We put in these coordinate points, 10, 10, 10, minus 10, minus 10, minus 10, and minus 10, plus 10. We have those 4 coordinate points there now. Turn on my cursor. And then we're going to connect these with a line. We have that there. All right, now I want to show you a couple things. If we come down here, there's some dimensioning tools. And let's see. Here's this one that says Auto Dimension. Select the entities to Auto Dimension. I'm going to just select all these lines. I'm going to hold down my Shift button as I select them so that they're all highlighted. And we hit Done, and it has these lines, and it shows that it's 20 millimeters by 20 millimeters. Now this parameter manager is kind of useful. We're going to select a dimension, and now it has this variable name as dimension 1, has the current value. If I want, I can change this to a different value and apply that, and it will change that and it will auto dimension it. Change it back to 20. And if I select this other dimension, I can put in an expression based on all these different mathematical functions for that value. So dimension 0 I'm going to copy and paste this. It's going to have dimension 1 times 2. Now I'm going to apply that, and then all of a sudden I have this way to build up different sized meshes and have it kind of auto-constrained. This might be useful if you're building a tensile specimen and have a radius of curvature that is determined by the diameter of the bar, for example. Okay, so let's just reset everything and go back to 20 by 20. Just wanted to show you that a little bit. Now this is all we need for the cross section. Oops, I'm going to do that. That's all we need for the cross section. So I'm going to hit Done. And the depth of this, we said we wanted it to be 400 millimeters long. Now twist, if you wanted to twist this maybe like a piece of wire, as it can twist about an axis, as a distance per revolution, you can specify that in here. We're not going to select any of these options, but we're just going to hit OK with the 400 millimeters. And we have that part that's been created. I'm going to go down to Properties, Mechanical, Elasticity, Elastic, Isotropic. We're going to put in 210,000 and 0.3 for our modulus of elasticity and Poisson's ratio. Now we do need an additional material property. If we want to edit it, we can click on it, Mechanical, and we're looking for density. It's under General. Here we're going to put in the mass density. It's a uniform mass density. You can have a distribution if you like. It can be temperature dependent as well. The number that we came up with was 7.9 times 10 to the minus 9, and again that's our consistent units of tons per cubic millimeter. That's a mass unit. We're going to create a section, solid homogeneous, using material 1, and we're going to assign that to this object. We go into the assembly. We're going to instance the part. We can make it a dependent instance. Now I just want to hit OK. I don't want to hit apply and OK. It will make 2 instances in that case. So I'm just going to hit OK. And if I open this assembly up, we see that we have this 1 instance in there. I'm going to go to the step. And this is going to be a little bit different than what we did last time. We're going to make a new step. This is going to be a linear perturbation step, and it's going to be a frequency type procedure. Continue for that. Description, you can put that in there. We're going to use the Lanczos algorithm. Subspace and AMS may or may not be available on all installations. Number of eigenvalues requested, all in the frequency range, is fine. And the maximum frequency of interest, let's say 20 kilohertz. So 20,000 hertz will be our maximum, and we'll hit OK. Alright, so we need to go to the next part, which would be, we don't have any interaction, don't have any loads, we're going to go to mesh. We're going to seed the mesh. Okay, and now if you notice, I'm in the part instance. I'm in the assembly, I need to go to the part instance and seed the part instance. I'm going to make this seeding size, let's make it 2. We'll see how it looks. If it doesn't run, we'll resubmit the job with a new seed size. And we'll mesh the part. Okay, let's zoom in on this a little bit. They look fairly cubic. Right, that's a good sign. If they were really stretched out, then we may have a too coarse of a mesh, and we wouldn't be able to pick up the nodal locations and the deformation behavior as it gets excited by its natural frequencies. So that looks adequate. I'm going to hit the X since I zoomed in on it, and I'm going to go down here to jobs. I'm going to create a job. We'll call it job 1 frequency. You can name it whatever you like. And it's not submitted yet, but if we right click and hit submit, then we'll get it submitted. Now this analysis may take a few minutes, and then we'll take a look at the results. There's a few things we want to mention while we're doing this though. The analytical solution that we got was for a beam, meaning that it was modeled as if it were a beam, and the type of modes that it would be able to calculate are the beam bending modes. When we calculate our modes using finite element analysis using these three-dimensional solid elements, the mode shapes that we will get will include the beam bending modes, but they will also have some torsional modes, and we'll see, since it's not constrained, some rigid body modes. So we'll talk about those. So the calculated mode natural frequencies that we get will be more than the natural frequencies than what we have determined for the first, what did we say, 5 modes for our particular beam. Alright, so now it's completed. I'm going to right click and go to results. It's going to load in the results file and expand the output database. I'm going to expand the steps, and I'm going to expand the frames. Now if you notice, there's 2 groupings of frames, 0 to 29 and 30 to 30. It kind of breaks these up in groups of 30. Frame 0, if we double click on that and look at the displacement for the contour plot of displacement, this is the undeformed mesh. Has no displacement anywhere. If we go to the frame number 1, double click on it, it has this nice color contour, But look at the frequency value. Frequency value says 0. Let me expand these so that we can see these a little bit better. And I always kind of forget where these are in, but let's go into Viewport Annotation Manager. No, that's not the right one. It might take me a couple tries. Viewport Annotation Options. Okay. And in the title block, let's set the font to be something larger, maybe a size 14, and let's see what changes with the title block. Okay, so this is the title block. In fact, we can just turn that off if we want. The state block is this one right down below it that shows the frequencies. So let's make that even a little bit bigger, maybe a size 18, so we can see that. All right, so we can turn off the title block if we want. And now we just have this with the frequency of 0 cycles per time. Let's animate this. We're going to go down on this one with the kind of the sine wave on it. Animate harmonic, and we're going to slow this down a little bit. And you can see it. It seems like it's rotating in space. There's no deformation that we can see in here, although it is displacing. There's no particular deformation that we can see. It's kind of rotating. If we go to frame 2, the other end is rotating, it looks like. Frame 3, it's kind of looks like maybe it's twisting and moving in space. For free boundary conditions, the first 7 frames, or the first 6 frames, will be rigid body modes. It's kind of a twisting mode again. Our first non-trivial frame then will be frame 7. Number is frame 7. I guess that's the 8th frame in the analysis since it starts with 0. So this is our first non-trivial natural frequency. And for this, it looks like we have a value of 653.3. All right, so let's compare that to our calculated value. Put it here in red. So our first natural frequency, we had 653. Let's get out the calculator and calculate a percent difference. Looks like about 1.2%. That's pretty good. I mean, this is going out to 3 digits, and it's changing at less than 10. Let me just double check that. Yeah, 10 out of 600. So it's a fairly small percentage change, percentage difference. So really, that's pretty good. Now, I do think if you use the smaller mesh seed, that you will get it probably a little bit closer to 661. Let's explore our other natural frequencies. So now I'm going to double click on frame 8. Okay, now see how it says 653.3, but the plane of bending is in the opposite plane of bending. So when we do this calculation that we went through analytically, this was assuming just one plane of bending. So we should expect to see an extra bending mode in the kind of the vertical direction in this horizontal direction. Frame 9, okay, now it's kind of taking the shape of a full sine wave. Its frequency is 1772. We calculated 1821. Right, let's calculate the percent difference in this case. I said 1772. We have a little bit higher percent difference. It looks like about 2.7. Right, now it's the other plane of bending with the same natural frequency. frame 11, 3398. That compares, I think, to our 3571. Although it looks like maybe it's bending in a kind of a weird plane. Let's rotate this around. It looks like it's kind of bending along a diagonal. So that may not be quite the one that we want, but let's explore this a little bit more. Let's look at frame 12. There's a 3398 again. Frame 13. Okay, now frame 13 is a twisting mode. So I think the previous mode was the one that we wanted to compare with our 3571. This twisting mode, however, is not one that our beam calculation from the analytical solution is going to pick up. So we'll go to the frame 14. Now we have 5464 as compared to our 5903. So we're picking up a little bit more of a difference between these. Again, I think it's a little bit sensitive to the mesh size, and as you'll notice, as we get higher and higher frequencies, the difference is a little bit more pronounced. Okay, so I guess that goes with the 5903. Okay, so that's about 24%. Let me try that again, just to make sure I punched all those in right. 5903 minus 5464 divided by 5903. I punched something in wrong. It's 7.4%. Okay, so the differences get a little trickier. So when you do a natural frequency analysis, this is one of the things you have to be a little bit careful about. At high frequencies, your numerical analysis may start to have some more inaccuracies than at low frequencies. For a car or something like that, you may be interested in frequencies that might cause some excitation due to your road travel. So a large structure may have some low natural frequencies that get excited just by running over strips on the road or something like that, and it causes kind of a buzzing sound. So you would want to avoid those kind of frequencies. Typically, the more mass that you add to a structure, the more you can change the natural frequencies. It's kind of the square root of the stiffness over the mass. So one of the things you can do in your extra analysis would be to change the density value and see how things change just from that perspective. Another thing you can do is change the element density, meaning make a smaller mesh seed and see how that will affect the results. See if you get more accurate results by doing a convergence analysis. And then you can also explore these higher mode shapes and frequencies. I'll let you take a look at them. So here's an expansion mode. This would not be a beam bending mode that the analytical solution would be able to calculate. And I want to point out the magnitudes of the displacement are all normalized to a unit magnitude. Because it is a free vibration problem, the magnitudes are not defined. They're the eigenvectors, but they've been made into like a unit eigenvector, a unit maximum displacement. All right. Let's go back to our model. Let me pause this. Keep that from animating. And I'm going to save this file, and then I want to look at one of the files that was created during this analysis. It's called the replay file. We'll just call that natural frequency 1. And I'm going to exit this, and I'm going to bring up an Explorer window in to look in my temp folder, so where all the files go that are created by ABAQUS. Now if you sort this by date, one of the first files you'll probably see is this abacus.rpy. That is what they call the replay file, and it's a Python script. We want to copy this, and let's rename it to nf2 script, or whatever you want to call it. We're going to open this with a text editor. You can use whatever editor you want. I don't recommend WordPad, but I'm using the Crimson editor. And what is in here is everything that we've done in ABAQUS CAE. Every mouse click, every dimension that we've entered, and everything else. Now, when we set this model up, we decided we were going to make it 400 millimeters long. Let's search for the 400. There it is. And I'm going to change this value to 200. If you notice, here's our material properties that we put in. Here's our density that we entered in. And down at the bottom should have been where we saved the file. We want to be a little careful. We're going to change this also to the file name nf-2. We're going to hit save. And we're going to go and restart ABAQUS CAE. And I may need to change the extension to a PY instead of an RPY, but we'll find out real soon. We'll X out of this window, come over here, and we should have an option to run a script. Let's see if this one works this way. Okay. So it's going to take a look for scripts, and it's in the temp folder, and I'm going to search for my star.rpy. I'm going to select that one, hit OK, and let's see what happens. Alright. Everything that I did, including submitting the job, so I probably overwrote my job, it's running right now, is going on right now in this script. And you notice it says down here, it has saved the file to nf-2.cae. So it's really important to make sure that you change that name. Now apparently before the job completed, it went and did the post-processing on the old file. So I guess you should be a little careful about that. But let's look at the results. It says the output database has changed. But now looks like in the output database and the steps, and let's see if we have a different value for the natural first non-trivial natural frequency. Now this first non-trivial natural frequency is 2547. Okay, so that's a bit different. Let's do our hand calculation and see if we get pretty close to that. Okay, so the only change I made was I changed this value from 400 to 200 millimeters, and when I calculated that out, I got a natural frequency of 2653. So that's compared to 2547. All right, so it went through and it did all of that kind of the blink of an eye, where it recreated everything that we did and started the analysis and everything. Now there's commands you can build in to pause and do different things, so it waits for an analysis. But this kind of editing the replay file to create a really quick script is very powerful. So every mouse click, every window move, every rotation, all of that just does it automatically. You know, you have to be a little bit careful about overriding things in your file, but that's a very, very handy feature. Let's go back to our model, and I want to see if I can find the place on here where we can change the first order elements to second order elements. Hopefully by the time we get to this point where this homework is due, we'll have a chance to have talked a little bit about first and second order elements. Let me write down the natural frequency. 2653 is what was calculated analytically. 2547 is what we had from our first order mesh. Alright, so I'm going to get back to my model. I'm going to get into my part. I'm going to go down to the mesh. Okay, I'm going to let's see, we're not going to reseed it, but let me find the right panel for changing this to second order elements. Alright, so I don't do this very frequently, but the panel we're looking for is this one. You see where it says S4R, assign element type. I'm going to select that, and then I'm going to drag a box around my entire mesh. I'm going to hit done, and it brings up this panel. And it has this element library. Right now we're using ABAQUS standard. We'll talk about explicit later in the semester. But here's the geometric order. Right now it's set as linear, but we're going to change this over to quadratic. We're going to use the reduced integration formulation for the hex elements. All we have in here are hex elements, but if we have wedges or tets, we can change those as well. We'll talk about these different options a little bit later. We don't have to worry about element deletion or degradation or viscosity, so we're just going to use the default on all that. So there's going to be C3D20R. Let's just explain the difference between 20 noded and 8 noded elements. Let me bring up the panel and let me save this. Find my writing pen. And I'm going to draw a cube, as we're looking at these cubic elements. Now dot in the hidden lines. If you notice, if you count them up, let me use a different color. If you count them up, we have 8 corner nodes. This is sufficient to define an 8-noded brick element. Now, the way that these nodes are connected are by straight lines. I'm going to see if I can just copy this picture. Just move it over here. And the thing that's different about what's known as the 8-noded and the 20-noded element is that in between each of the sides we have additional nodes. So now we have 8 plus 4 more for these side nodes, plus another 4 for those sides, plus another 4. Okay, and if we add that up, that should add up to be 20. Now, reduced integration is something that we'll talk about later as well in class. Reduced integration has to do with the integration scheme for the elements based on the Gauss points in the elements. But the feature that's relevant to us right now is that these have the ability to have a more complicated deformation field. So when this deforms, we're going to have a straight line between those two nodes. Okay, so this is like node A and B. we'd have a straight line from A to B. When this deforms, let's call that A and B, we have 3 nodes, so we have the ability to fit a cubic through there. Instead of just a first order line, we can fit kind of a cubic. So the way that it can deform along that edge is a little more sophisticated. You also have the ability to capture initial curvature easier as well. Alright, so let's go back to our CAE file, our CAE model, and we just changed this to quadratic. I said cubic earlier, I meant to say quadratic. It's quadratic element, so we can fit a quadratic line through it, not a cubic. And I'm going to hit OK on this. Now we change the order, so let's go and let's resubmit this job. We'll just overwrite those results. I have the number written down. Let's see if this changes the accuracy. Now there's a couple reasons why you might want to use 20 noded elements. One is for a coarser mesh you can get more accuracy. And that's the main reason, I guess. The other is for more closely following the original geometry. If you remember back to our first homework problem, we had the pipe and the edges were kind of flattened. We can more closely approximate a curved edge for our original elements if we use quadratic elements. Right, so this is running. We'll let this go for a little bit. I suspect we'll be a little bit closer. And so instead of changing your mesh density, you can change your element order, and you can try to find quicker convergence. There is a computational cost to using higher order elements. You also have larger input files to deal with if you need to edit them by hand or take a look at them, and they're a little bit more complicated looking. So it's still kind of a trade-off between efficiency and computational cost. I'm going to pause this while this completes. Alright, so it's completed. Let's load up the results. Get into our frames, and let's see, let's look, I guess we decided frame 7 would be our first non-trivial one. And now we've got the answer of 2561. Right, so it changed from 2547 to 2561. So we got a little difference in that finite element calculated natural frequency. Now it's still not super close to 2653. Let's go ahead and calculate the percent error while we're here. 2653, 2561. It was about 3%. Now one thing that you'll notice if you change the lengths, this is now a 200 millimeter long beam, is that you'll start to be less beam-like when you get shorter and shorter lengths. Right, so what I'd like for you to do will be to try a series of different lengths, maybe shorter or longer lengths than 400 millimeters, and see how that influences the first maybe 3 natural frequencies that are calculated, and try to put together a report on that. All right, so now that you've got more experience with ABAQUS, I'm going to ask you to do more things than what I'm going to show you. So we'll just kind of build our knowledge and our experience with ABAQUS in that way. Of course, if you have any questions, please contact me.